Hello, everyone. Welcome to On Air, the online program of the Swiss Air Weeks and Wildcard Media. Today we have an exciting program, AI for Space, lifting off with AI from Earth to space, a 2-hour session with two different panels. I do it very short, and I hand over directly to Valentina Tumburella from Ateleris to guide you through these two exciting sessions.
Thank you, Tilman. Thank you for the introduction. So, hi, everyone. Welcome also from my side to today's session on AI for Space. So, this is, as Tilman said, an AI event, part of the Swiss AI Weeks. It's organized by Ateleris with the contribution from different institutions and companies you will learn about in a minute. So, thanks, first of all, to Tilman and the whole team of the Swiss AI Weeks, especially to Sabine for the opportunity and for the support that they gave us already through the event organization. So today I'll be leading you through the full event, and together we will have the chance to explore how earth science and also space exploration are entering a new era thanks to the use of the AI. Indeed, with your satellites producing tons and tons of data and the spacecraft, the space mission become more and more complex and autonomous. And with humankind venturing further away with the space missions and with the human exploration, AI is providing to be not just useful, but really essential and fundamental in this step. So for the next 2 hours, we will have, of course, a break in between, and we will explore how AI is transforming basically two main areas. So you saw in the description that we also have a part about the use of space data from satellites orbiting our planet and other spacecraft, where AI can really help with filtering and analyzing the large data sets that we have. And the second part will be about the space operation, where autonomous systems must adapt, self-correct, even make critical mission decision. So the event is divided into two sessions. Both of the session will start with the presentation about use cases and the current technologies, and then we will start with the panel discussion with experts and the final Ask Me Anything session. So for the audience, you can interact with us through the expert directly through the chat. So feel free to. We will not pick up questions directly after the presentation and during the panel discussion, but we will reserve the last 10-15 minutes of each session to answer the questions that you can write directly in the chat. So with this, I would like to start immediately with the session 1. And so we are going to focus on the use of AI on ground to analyze large space datasets. So it's my pleasure to leave now the floor to Jasmin Katzenring, a postdoc at the University of Zurich Remote Sensing Lab, and to Gaetan Petit, who is the CEO of Ask Earth. So just a brief introduction, Yasmin has a PhD in remote sensing. She will give you an overview about the challenges that we can face thanks to large datasets of satellite data. While Gaetan, he's the co-founder of Ask Earth, a software company which uses a large language model to extract information from satellite images. So he will tell you more about the technology development to improve the analysis and make data accessible to everyone. So with this, I leave the floors to Yasmin and Gaetan. So please, I'm going to mute myself.
Hello. Do you hear me now?
Very well.
Okay, perfect. So I quickly have to share. 1 second. So. Do you see it now? Perfect. Thank you. So thank you, Valentina, for the introduction. And in this presentation, I will talk about the concept of biodiversity and how we can use Earth observation data to monitor different aspects of biodiversity, and how different methods such as deep learning can help in analyzing the vast amount of available satellite data that you just mentioned. And for example, here I have the Sentinel-2 shortwave infrared false color composite in the background, which is showing the differences of a peatland in in the Siberian tundra. And now I would ask you of thinking about whether you know or you could explain someone else what actually biodiversity means. I give you some seconds to think about it. And I also asked Gemini the very same thing. So I asked it how it interprets the term biodiversity and make a figure from it. And this is what it showed me. Or not. Now it works. So I would say that it mainly shows the species diversity. So how many different species are there living in a specific area? And in this image, especially the animal species diversity. And probably this is also what many of you were thinking about. However, the concept of biodiversity incorporates much more than just species diversity. So the Intergovernmental Science Policy Platform on Biodiversity and Ecosystem Services, or short EPBS, defines the term as the follows. The variability among living organisms, that's what we saw, from all sources including terrestrial, marine and other aquatic ecosystems, and the ecological complexities of which they are a part. And this is probably also how Gemini interpreted the data. But there is much more. So the biodiversity includes variation in genetic, phenotypic, phylogenetic, and functional attributes, as well as changes in abundance and distribution over time and also space, within and among species, biological communities, and ecosystems. This means we don't only have the concept of the species diversity, but we also take into account, for instance, the genetic diversity. For instance, if you have two dogs from the same species, they can still have different colors of fur, for instance, so they are different from each other. And lastly, we have the functional diversity, which which describes the function within ecosystems and between ecosystems and their parts within the ecosystem. So trees of the same species can have different functions in the ecosystem, and they can have also different traits, like they can have different morphological traits, so they can be of different size, even if they're the same species. They can have different physiological traits, so such as different water contents or different pigment concentrations. And they can also change how they look like over the course of a year, which is like the phenology. So to effectively conserve the biodiversity, we first need to be able to monitor its status and the trends over time. And for this, they developed the essential biodiversity variables. They are a set of parameters that capture the key aspects of biodiversity, so from genetic diversity to ecosystem structure and function. They aim to analyze and standardize the measurements that we take, which we then use to report and manage changes in biodiversity across time, space, and different levels. And this is exactly where now the Earth observation data comes in, because the advantage of the Earth observation data is the global coverage and the long time series that we have, and that they provide us with regular revisits from the remote sensing satellite data. And this data can then be used to fill gaps in biodiversity monitoring and showcases also the changes over time much more figuratively. In this figure, you can see some examples for remote sensing biodiversity products. So in the left box are the 6 defined EBV classes. In the middle are EBV candidates that contribute to each of the class. And on the right is one example of how we could use a remote sensing products to describe these candidates. Of course, there are many more for each of the candidates. And researchers here at the remote sensing laboratories at UZA are working mostly on the trait-based functional diversity, and also develop methods to monitor genetic biodiversity indicators to fill this empty box that you see there on top. And to calculate the biodiversity products, we mostly use passive optical data from satellites, from which we then can derive land cover maps or functional trait indices, such as water content or chlorophyll content. And if available, we can also use LiDAR data, which is 3D point cloud data, to derive morphological traits, such as vegetation height or density. And there are many freely available data products, and mainly from 10-ish passive optical satellites, which gives us already a huge amount of data. And the Sentinel-2 satellite constellation alone acquires about 15 terabytes of data within 5 days, which is the time frame that it takes them to map the whole Earth once. So if you want to monitor changes over long time periods or like in large areas, you quickly come into this issue with too much data to handle. And this is where we can use machine learning or deep learning algorithms, because they are able to handle such large amount of data, and they can also help us to automatically detect patterns or changes in our data and flag it for us to further analyze certain parts. But they can also be used to do image pre-processing, such as cloud removal or data fusion, image reconstruction, etc. There are 4 main application classes or uses in remote sensing. So the first one is simply classification, so the labeling of single images, for example, as being cloudy or as change was detected. So in this example here, the blue square indicates or labels this image as cloudy, and the red one is the same place, but it is not cloudy. The second one is segmentation, where we use, for instance, semantic segmentation for pixel-wise land cover classification. So each pixel is assigned a class. So for instance, here is the land cover land use map derived from Sentinel-2 data. Then we can also do object detection, so label or detect specific objects like different species. And this is more used in high-resolution imagery. So in this example here, you see they used high-resolution data to detect and count whales in the ocean. And the last one is regression, which is the prediction of continuous variables, such as vegetation height, for instance. And I will show you this last example in a bit more detail. So in this work, they use Sentinel-2 data, so optical data, to estimate the canopy height of vegetation, which is like a 3D parameter. And this canopy height estimation can be very valuable because we can get information from it like biomass, or let's say like here, the above ground carbon of this biomass. And it is also important as it is an indicator for the morphology of the trees that we encounter in the respective pixels. So in the left image here, you see the derived canopy height that we got from Sentinel-2 or from their model. And on the right, they're calculated above ground carbon. And this is in a very dense forest in northern Borneo. To achieve this, they developed a probabilistic deep learning model to combine both the space-based LiDAR data from the Global Ecosystem Dynamics Investigation, or GEDI mission, with Sentinel-2 data. And they did this to have, like, the aim of it was to gap fill areas where there are no GEDI data. So like between footprint acquisitions or outside of the actual GEDI acquisition area. Because as GEDI is mounted on the International Space Station, it will never be higher or lower 51 degrees north and south. And from this data, they then estimated a global canopy height model map. And you can observe that the results are sometimes good, but sometimes also biased. And this is exactly in these areas where there is no JEDI training data. So out like above this 51-degree border, with like high tree heights in, for instance, Scandinavia or like Alaska, which should not be the case, as there are not that many high trees as in the rainforests. And this leads me to my take-home messages already. So the machine learning or deep learning methods are of really great use for us to study the vast amount of Earth observation data that is available. And they can also provide important products and maps for biodiversity monitoring, such as the canopy height map that I just showed you. But it's also very important to think that scientists and experts in their respective fields are still needed and very useful to validate the generated products and assess whether they are actually useful and whether they make sense. Thank you for listening.
Thank you, Yasmin, for this great introduction to what we can do with satellite images. You're going to make my life much easier for my presentation. Happy to see you all. I see some familiar names in the attending list. It's great. I'm looking forward to your questions and the discussion afterward. Thank you also to the organizing team for inviting me today. I'm Gaëtan Petit. I'm very happy to represent our company AskEarth today. We are sitting in Zurich. We are a spin-off from different universities, University of Zurich, also the group of Yasmin, but also ETH and EPFL. And we have a few research projects with the European Space Agency on the topics of large language models or foundation models for satellite images, but also GIS or geospatial data in general. And I'm happy to tell you a little bit more what we're doing at AskEarth. So we can go to the next slide. So Yasmin did a great presentation about what we can do with, machine learning, AI, and satellite images. But just to recap that a little bit, 10 years ago, I think it was the hype of neural networks and training machine learning models on many data. There is a lot of great models out there. Yasmin showed some of them to do classification, to decide what is the main thing we can see on the satellite image. Is it a forest? Is it a road? Is it buildings? Or object detection on high res. So is there a car or building on the picture? There is great models out there, and this is not new. And so far, it's still the best model that are out there to do this type of tasks. But about 5 years ago, there was a big transformation and revolution in the AI industry, or AI research industry, at least. It is the foundation models, and I think there will be other presentation about foundation models today. Which you all heard about with large language models or ChatGPT, which is the main, application that everybody is using on a daily basis now. But this was very different than what we had before. Before, we were training models for one use case, for one specific tasks, and we had the best models to do that. That's neural networks or deep learning, and with foundation models or large language model, we had something more general that could basically answer many more questions that we could apply to other use cases and would still perform pretty good, but maybe not as good as a model that is, trained for something very, very specific. And what we see today in the field of satellite images or of observation is the emergence of vision language models. I think there will be also a presentation on that. I won't go technically on this topic, but maybe the follower speakers will do. But this is very promising as well, because large language models is, as the name states, for language. So it predicts words and the language field, but vision language model predicts images, and satellite images are images, and today we can do prediction of satellite images. The models are popping out every week these days, and it's very promising and growing very, very fast. We're looking forward to see where it's going and use it as well. But I would say for a very specific task, the deep learning or neural networks are still more accurate these days. So just that was a quick overview of AI in general on the topic of observation or geospatial information. So Yasmin, I can move to the next slides. So at AskEarth, we have been leveraging this trend. We created a company about 3 years ago where a large language model starting to be good. And we wanted to apply this technology to satellite images. And I will show you a little bit how our agents work. So the agent, the product that we've been building at AskEarth. The reason why we did that is because customers or large companies, or our customers basically, are large companies with a lot of information on the map. So they have assets to monitor or predictions to make on these assets or goods that they want to monitor. And yes, there is specialized people in large companies, and there is some today as well. But everybody in the company doesn't really know how to analyze satellite images or GIS data in general. And these people that are not specialists, they want fast answers to their questions. And we thought the best way to give them fast answers would be to put a chat and a map together and analyze satellite images through that. So I will show you now a small demo. If you go to the next slide and the video. This is a use case for an insurer that wants to monitor the impact of their assets or buildings from a natural disaster, here a wildfire in LA last January. So we have data from which buildings have been insured in this region. And within a few questions in chat, you can see in green here, the user that is not a GIS expert can ask a few questions and get access to the buildings that have been insured, but also the area from public data that has been impacted by the wildfires. Sometimes this area are not specific enough, so we need to upload satellite images from Sentinel-2 that has been explained by Yasmin before, where we can watch the difference between before the event and after the event. And we have, our agent has access to a few algorithms to basically process the damages of this wildfire in the region. But where this becomes very useful, this agent and this chat interface, is to actually get insight out of this analysis. So analysis of satellite images is not really the center of this application. The application is what can you get out of it. And what an insurer wants to do, especially if he's not a GIS expert, is to know how his assets are impacted by that. And what we can do here is we can upload also all the contracts, all the PDFs, all the documents of the insured buildings there. And once we know how much damage there is, we can also help the insurer decide or figure out how much they will need to unlock to help the people around there and take a faster, more informed decision without having to involve the GIS or the geospatial team within the company. So that's a bit what we have been building at AskEarth, a tool to make the data more accessible and to help people get better and faster insights and take better decisions based on that. So you can move to the next slide. I will give you, and for the people that are in the field, please do ask questions later on, a bit of a breakdown on what is in the back of our agent. So we have built an agent called GIA, a Geospatial Intelligent Agent. And at the top of this graph, if you see the user that is asking a prompt is basically a text that you would put on ChatGPT or on our tool. The text is then analyzed by our agent GIA, which use the capacity of large language model to do structured reasoning, to take decisions. And we use that to basically choose the best algorithms. So this can be neural networks, deep learning, or EO foundation models now, and the right data to answer the question in the best way. So every time there's a question, we can build a new workflow on the fly to answer the best way possible the question from the user. And what is very important for us is to give transparency into which tools and which data has been used, because people don't always trust AI and they want to know what data and what tools are used. And we give full transparency to the user there, and the user can ask as many questions as they want if they're not happy with the answer until they get the right answer there. Next slide, please. Again, just a different visualization of the same thing. So at the top, we have our agent, GIA, geospatial agent, which for each question will select a number of tools and a number of data sets that make sense to answer this question. And the workflow and the path to these things is basically different at every question. And that's what we've been building. Why we've been building such an architecture and not just feeding all the data to the large language model like you would do if you go on ChatGPT, just upload an image or upload a document there. It's because satellite images are very heavy. You don't want to analyze satellite images with an LLM. It would be too slow and too costly. And if you feed all your PDFs and all your documents directly to the large language model, We also create hallucination. So basically, hallucination is the LLM or the chat GPT trying to invent or predict the information, and that's not what we want. What we want is only leverage the data that actually exists to give an answer that is correct and not invented. So that's why our architecture is like that. Yes, you can go to the next one. It's perfect. And this is my take-home message and conclusion. So we've seen the things changing quite fast in the last years in the field of Earth observation and AI, from deep learning to foundation models with large language model, and now vision language models that are growing very fast at the moment. We are onboarding all these tools into our agent, and we're really happy to see the research community building more and pushing the boundaries of what we can do with AI these days in the field of remote sensing and Earth observation. So thank you so much for your attention. Looking forward to the Q&A.
Thanks a lot, Yasmin, Gaetan, for very interesting overview on the satellite imagery and technology as well. So as I said, we don't have time right now for the question, but if you have question for the speaker as well, please write them in the chat. We will have time after the panel discussion. So with this, I'd like to move directly to the panel discussion. And so let me introduce very quickly who are our panelists today. So we have, actually, I have even here in the office, Simon Felix. So he's the co-founder of the software engineering company Ateleris. He's a lecturer and senior researcher at the University of Applied Science, Northwest Switzerland. He has been developing commercial and research software. So he will be our technical expert. We have also Cyprian Tomoyaga. He's a research scientist for AXA Group, so he's focusing on bridging the latest research in computer vision and LLM models into insurance use cases. Welcome, Cyprian. We also have Valerie Termaten. She's currently doing her PhD in the field of deep learning for Earth observation at EPFL. And finally, we also have Henry Martin, a member of the technical staff at TUA, a company pioneering general purpose foundation models for Earth. So, and with this, I would like actually to start with you, Harry. So with Yasmin's presentation, she showed several cases related to the biodiversity and something which is more Earth related. But at you, I saw your work focus on training models on space data to enable some accurate weather predictions, which is something that we have not touched yet. Also in the presentation from Gaetan was something missing, but for sure very interesting. So could you share an example of your work and tell us which kind of data you use and how you are using the AI in this sense?
Yeah, thank you. Yeah, sure. We built a global weather forecasting model at high resolution. And for that, we have several use cases for satellite data. So with AI-based weather forecasting, one thing that's important, how we can use AI for that, is that we don't have the same limitations as classical weather forecasting models that require to explicitly solve a very large set of partial differential equations. And so this limits the scale and frequency that these models can update. With AI models, we don't have these limitations. For a very long time, AI models were not able to be as accurate as classical weather models, but about a year ago, when we published our first model, EPT 1.5, we could break this point even and go even beyond the accuracy of numerical weather prediction models. And then what we are working on now is to also to be able to update these models as fast as possible. So due to the computational constraints of classical weather models, you're only getting 6 global weather model updates a day, because it just takes so long for these models to run. But now we are able to run them in minutes instead of multiple hours. And in order to be able to give you really the weather forecast based on the state of the Earth that we have at this point, we need to make use of all the information that's available. So this means weather stations, past forecasts, but very importantly for weather forecasting and Earth observation is the data that comes from satellites. So for us, it's really important to have a look at all of these satellites. How can we use this data with as little latency as possible, and then getting them into our model. So these large AI weather forecasting models are usually based on like large transformers, but it's not so easy so that they can natively understand multiple satellites. And so this is a big topic that we're currently working on, is how is it possible that we can take in all the live observation data that's currently available from different types of satellites. So Jasmine mentioned these passive observing satellites, but then also microwavers or active satellites, to have all of them together, fuse them, and design a multimodal learning problem around them, so that we can really, at any point in time, basically just collect all the observations that are currently available and launch the freshest weather forecasting run that's possible.
Thanks a lot. So you work a lot with real-time data. So, but for example, this trigger another question maybe for Cyprian. So you work at AXA, so it's a big insurance organization, right? And the risk factors there are really important. So you probably work a lot also with the historical data more than with the real data, like in the case of Henry. So what kind of risk can you assess with space data? I think we saw already something in the presentation from Gaetan with the example of the fires in LA. But what kind of application with use case do you have also in your case?
Yes, Valentina. So, like you said, we traditionally based a lot on historical data, but we are excited with AI models because now we can also put different conditions. So, besides, like you said, various risk factors like wildfire, we can detect, but also various objects like what could cause these wildfires. Maybe we want to find propane tanks next to flammable materials. Maybe we want to find electrical towers that are not well maintained, and then they could start a wildfire. So these are the kind of risks that we're trying to find with AI. But I'm also excited about what Henry just presented, because his models being able to run fast, maybe in seconds or minutes, would allow us to run simulations, which with traditional models is not possible. So if we want to maybe say, what will the climate of 10 years from now impact the people, the society? Maybe there will be hurricanes where there have never been hurricanes. So historical data is no use there. So we cannot protect those people. But using models such as Henry's, which can then simulate various paths of hurricanes, maybe later on, we could protect these people better.
Yeah, maybe I could jump in there directly, because this is something very exciting. Because currently, as you said, these models are faster, but still not fast enough. So usually, what's done to simulate these very large horizons that you need so that they're interested for insurance companies, so 10, 20, maybe 60 years or even further, you would only run these reduced capability climate emulators. But I think fundamentally, there's no limit why we shouldn't be able to make a 100-year weather forecast if the models are good enough. So then you would really get access to all the information, like really seeing individual hurricanes or individual thunderstorms, instead of just these maybe global temperature averages that other models would output.
That's very interesting. So maybe not to jump too far away, but to also see another aspect of the data that we are using. I would ask Valerie, so in your PhD, you're not using only satellite data, right? But you are integrating also some citizen science observation. You're using different platforms. I remember Design Ateleris, Beard. But how does this help, and why do you think that crowdsourced data are so valuable in your case? What kind of different information are bringing them in?
Yeah. So during my PhD, I'm working on ecosystem mapping. So the task of ecosystem mapping is quite similar to land cover mapping, except that we want to be a little bit more precise. So for example, instead of predicting that is a forest, we want to know which type of forest it is. And in some cases, satellite data are not enough to tell apart different type of ecosystems. So we need to have access to other type of information. So in my case, I use ground level observation of species. So like you mentioned, iNaturalist, eBird, or for example, PlantNet data. So that are crowdsourced by people. So for example, people that like to go hiking, take a picture of a plant or an insect, then it's identified and geolocalized. So many people like to do it. And we as a researcher, we can use those data because the presence of certain species are an indicator, strong indicator of the type of ecosystem that are in certain location. So we really like to use those citizen science data because they are usually available for free at large scale, and they provide information that we cannot see from the aerial perspective. Yeah.
What do you think? I mean, maybe this is a question for Simon here, and I mean, for whoever wants to answer. So, I mean, with using different sorts of data, I mean, these are about satellite data or drone data, crowdsources data. So, from a technical perspective, I don't know, Simon, for example, what kind of risk, challenges, or benefit are there? Is there something that we should put attention, because every time that we manually label some data, we are not sure about how well this data are labeled and how can be used. What would be the risk and what are the benefits in your opinion?
I think labeling is never perfect. So even if you have experts telling you something about the data, humans make mistakes. So only about 95% or so would be labeled correctly. And the same applies for citizen science projects. If you ask lay people to label data, they will not get 100% accuracy. But what you can do is, when you have a large citizen science project, is you can verify that people are well-intentioned. For example, you can check for intra-participant reviews and see if the same person answers the same question twice the same way. You can also check whether multiple people agree on the same facts or not, whether and using statistics, you can weed out bad actors, so people that purposefully try to distort your data, or maybe even people that misunderstood the rules. And if you do those statistical analyses and filters, the data from citizen science projects is usually of very high quality, sometimes even better than expert labeled data, because you get so much of that data that helps enormously. And then the other part of the question that you answered, how to integrate drone data and things like that, I think Henry can maybe also add to that. I think the difficulty is that you have different resolutions, different time scales, and so on. And some of these models rely on specific grids on a specific resolution. And then if you combine multiple data sources, you have to align all those data sources and normalize them to a specific standard. And that typically means you lose some of the details from one data source to another. But Henry, maybe you have more to add there.
Yeah, exactly. This is exactly the, let's say, classical approach, that you try to put everything on the same grid, but then you lose information when you might be interpolating maybe. And then it's also not scalable as much, because it's a lot of pre-processing work. And then you also force some data into representations that are not natural for this data. So typically weather stations would then be very sparse on a large grid. And the key for the success would really be to encode the data, and so that the AI model gets all the information it requires about timestamps, temporal resolution, frequencies, and location, so that you can then combine it automatically, basically, in the same embedding space. So let the AI do it, basically. let the AI do it, I think is also very important for this integrating very noisy or citizen science data. So I think in general, there's a lot of potential in adding all this data, but at some point, at some scale, it will not be possible to manually weed through it. And in LLMs, and we do the same thing, but for sensor data, there's great success that you let your model do it. So typically, GPT-2 would like correct the data for GPT 2.5. GPT 2.5 would correct it for GPT-3 and so on. And then the same we also have to do for Earth observation data.
Yeah, and a challenge in the same, maybe related to putting data together for me is I feel sometimes there are some, apart from bad actors, there are still some categories which are missing, some which are very specific. I'm wondering if Valerie has seen these. Do you think there will be a specific plant which you know is there but people never get, or or like if you're trying to put together, you would have errors that accumulate also. So if you have a model that is predicting the plant that the person is taking a photo of, then if an error in this model will produce an error further on or more errors in the big model. I'm not sure if any of you has dealt with this, either error accumulation or categories which are completely missing.
So maybe in my case, I have rather the inverse problem. So in the case of people collecting too much data in some location, then we have biases towards some specific type of ecosystem. So because those crowdsourced data are biased toward different geographic locations, specifically places with high population, basically closer to roads and hiking paths, we have more data. And then if you're there is a north-south, at global scale, there are more data in richer countries. So also it's those kind of biases that we have to take into account when we train our model, that area with more data are maybe better predicted that area with less data, and also random biases where people take picture of the plants in their garden because they really like them and maybe not the actually useful plant for predicting ecosystem or biodiversity. So there are like many different biases that can, a bit transform the data, and we should really be careful and filter nicely the data before feeding them to a model.
This we were talking a lot about filtering the data and having a really many data. So what do you think about, and this is an open question, I mean, it could be maybe for Henry, because you also have to work with real data. So what do you think about pre-processing, for example, and embedded applications? Because this is something that we are now focusing on, really analyzing the data on the ground, but on the other side, could be maybe a possibility to have some sort of pre-processing already on satellites, for example.
Yeah, so in general, we're quite skeptical of pre-processing because we need the data as fast as possible, because otherwise it would be aged. And then typically how it was in the past is that this data is sent to the ground stations, collected, and then pre-processed. And then we would rather use, or at the moment we are opting for using the raw data sets just because they are faster, even if this is a higher, let's say, pre-processing workload on our side. And there, I think these pre-processing on the satellite system or on the satellite has a lot of potential because it's way faster, and then we would get much higher quality data in the same speed. So this would, I see, like, there for us as a, let's say, end user would be great potential to, or would be great to have it. I was just wondering always how much you can do it without biasing the data towards a certain extent. Like if it's still possible to pre-process them such that they are generally applicable without losing too much information.
Maybe I can jump in here. I worked a bit in this field, and I'm also skeptical. So I share your view, because there are multiple applications for AI in space. And one thing that is useful is data compression, because AI can predict what typical data looks like you can squeeze it that much tighter and send more data. And I think that's a useful application, and you can even you can build it in such a way that you don't lose any data or any information, and then it's good. But if you do anything else, you run into issues. You don't have enough power, you don't have enough cooling in space. So those are big problems. And also, you typically want all the information, every last bit of the image that you can get the highest detail and so on. And if you pre-process it, you risk that you lose some amount of data. So people, especially in the scientific community, they want the raw, unchanged data. Not for performance reasons, but because you maybe 10 years down the line, there's a better method to squeeze out more information from those images and measurements. So that's why we tend to refrain from doing AI in space. But I think there is a use if you are doing a deep space mission where you have downlinks and it takes you 30 minutes to send a command to the spacecraft, then that's a good use case for AI. So the AI can autonomously do and decide in space.
Sibra, do you want to add something about this? Do you also share this opinion about the preprocessing, or is something that could be applied differently in your case?
It's new restrictions that I'm learning. So yeah, I wasn't aware of the cooling process. For me, it would be useful, yes, to have it a bit more processed, so I don't have to refilter all the cloudy images that was shown before every single time I'm doing a new task. Every time I decide, oh, there is a new object I want to detect, I again have to start over filtering out the clouds, processing and everything. So yes, being it filtered as a source or somewhere earlier would be useful. But then again, yes, it does require the entire community deciding, yes, cloudy images are not useful, maybe, but maybe down the roads, oh, Henry will want cloudy images to see the thickness of the cloud. I don't know. We don't know.
But cloud removal could also happen on the ground, right? You don't care whether it's done in space or in the ground segment.
Unless it comes at you could replace it with something else. Maybe we're limiting how much data, the areas that we capture, right? You can only capture so much before the next transmission. But if some of them would be filtered out in space, you would have more of the interesting areas. Maybe today we don't capture a lot over the water. We're focusing mostly on the land mass. I do have some use cases in mind for things we could detect on the water. Pirates, yeah, no-go zones, stuff like that. So, yeah.
So thanks a lot. I see at the moment that we don't have a question in the chat. I just repeat for the participant or maybe who joined later, if there's any question, you can write it there. Actually, there's already one. So Global Bandwidth, working with satellite images, how to successfully remove clouds in a smart way. Well, I think Cyprian, since you have a lot of experience in removing clouds, maybe you want to answer.
Yeah, I can start, but surely others have more experience. It depends a lot on your source, basically. I think in Sentinel-2 data, this would be quite easy. You have a lot of bands that would help you find out the clouds directly. Otherwise, there are now some specialized models, I think one even by ESA, to mark clouds in satellite, ignoring the satellite source, basically. So in any kind of image, you can detect clouds. But I don't think there is an easy one. There are also some see-through clouds where you hit the edge cases of whether you want to completely remove this image or just to enhance it to see basically better through the cloud. I'm not sure if any of you have more experience, feel free.
No, I think as you said, we really want to keep the clouds. So I don't work so much on removal.
And there's another question, what resolution is the most available for ground observation to employ resolution increasing algorithms? Well, here I think it depends on the scale of the problem you're looking at.
Yeah, exactly. I think we discussed this quickly in the preparation. so we employ resolution increasing methods, but we are operating on a different scale. So classical weather models, they're more on the global weather models on like 10-kilometer scale. And then now we are able to go down globally to 5 kilometers. But that's not what you would consider as a high resolution for real ground observing satellites, right?
Yeah, so maybe I can jump in. So there are a lot of sources that will give you multimeter resolution. So a single pixel corresponds to meter or something like that. And I think the better, more modern satellites give you up to 50 centimeters resolution per pixel for commercial applications. That's those are the products that I'm aware of that you can easily buy. And then if you do super resolution on top of these images, you can go a bit higher than that. You can get a bit higher resolution, but you always run the risk that the model invents things that are not there. And because the model essentially just guesses what could be there, and it gives you one of those options. So that's rarely good enough. So counting car works, or doing things on that scale. If you go much below that, things are not realistic at the moment.
And then we have one last question before the break about the synthetic data. Can we work with synthetic data if data are missing? Is that reliable? Well, this is I don't know, Valerie, if you have an idea, since it was the direct question that Cyprian also had to you, or if somebody else wants to reply about this.
Just very briefly, you should mute your mic. So IBM has a model published a couple of months ago called TerraMind, and this model accepts multiple channels and will give you realistic approximations of missing data. So you could use that to simplify your data pipeline, but I don't know how accurate it is or how reliable it is. I've never used it personally.
Yeah, personally, I also haven't used it. So personally, also never use synthetically generated data. Mostly because when you generate fake data, it's basically you copy, like to replace, for example, missing data, you copy something that the model has seen during training. So it's like we saw during the talk before, it's a copy from something of the training set, and we are not really sure what, and it's hallucination. So we can fill the gaps for like a visual perspective, but then using a generative model for getting scientific knowledge about a place, I don't think it's working at the moment.
So for weather forecasting or weather time series, we often use infilling there are a lot of very rich climate simulation data sets, which have 2 cores of a temporal resolution. And then we can use our model to increase the temporal resolution. But I think it's maybe a special case because we have like the physics as boundaries. And so basically our model can fill in the missing time steps in between the given time steps, but such that it's still physically viable.
Very good. So with this, I see the time. I see that it's 5 minutes to 3 when we are starting the next session. So I saw that there was another question, but maybe we can keep also for the second session, as we will have some people also working on security. So I would like with this to thank all the panelists and the speakers for this great panel and this great presentation and overview about the satellite imageries. We learned that basically it really depends on the use cases that we are looking at, and that's still pre-processing can be useful indeed for some people, but not for other use. So I would like to now stop here and have just 5 minutes of break. We will start immediately at 3 with the second session, so we give the time to the speaker and the panelists to exchange. And still, if you have questions, feel free to write here, because some of them will stay anyway until the end of the event. So you still may have a possibility to ask your question. Thanks a lot. Thanks Yasmin, Gaetan. Thanks to all the panelists. It was very interesting.
Thank you.
Thank you.
Thank you. Bye.
Okay, so time to start again. So we start immediately with the second part of the event, AI for Space. So in the previous session, we saw how AI can help analyze a huge amount of space data, and we saw about some limitation and some advantages that could be represented by the processing, by the use of synthetic data and more. So, but during the panel discussion, we see also the enormous advantages to use AI also directly on board of satellite, especially in the case of autonomy for the spacecraft itself. And so it would be also very useful in other situations, like for example, early warning system and where fast reaction is needed. So in this second section, we will focus on the use of AI really in space, in the space environment. So we will start again with a joint presentation, and then we will move to the panel discussion, and we will have again time for the question later. So for the people who just joined, just be reminded that you can always write your question directly in the chat, and we will take them after the panel discussion. So for this joint presentation, we will start with Hee Wang, who works as Associate Program Officer at the Climate Risk and Early Warning System Initiative, the CRUISE initiative. He is supporting the design, implementation, and monitoring of risk-informed early warning projects in climate-vulnerable countries. So as in session 1, the presentation will be followed by the technical perspective. This time will be done by Laszlo Etezi. He's the CEO and co-founder of Ateleris, a software engineering company which is trying to accelerate the use of AI on board of spacecraft. So if you want, the floor is yours, and Laszlo, we continue after your presentation.
Thank you very much, colleagues. Thank you, Valentina. Hope you can hear my voice. That's before I start. Okay, thank you very much. Yeah. Without further ado, good afternoon, everyone, and thank you to Ateleris and the Swiss AI Week organizer and partners for inviting us. So my name, as introduced, is Hee Wang. You can call me E or Ivan, with Climate Risk Early Warning System Initiative, CRUISE, at World Meteorological Organization, where is our office based in Geneva. And today I will share how CRUISE can help the most climate vulnerable countries build early warning systems, and how artificial intelligence and space technology can help us scale this system so that everyone is protected. Next slide, which we will show according to UN report stats, that there are still more than 70 countries in the world are missing adequate multi-hazard early warning coverage, our systems, and how we are going to achieve this is always our goal with UN, global, regional, even local partners. And here, as you can see from the chart, that's a value chain on how exactly we are achieving this. What we need is more than just the weather model, and it crosses different sectors. We need financing that reaches the last mile, strong institution that can sustain service, and new tools like AI, Earth observation to overcome capacity gaps. And CRUISE act as a catalyst and a bridge between those need and resources, and partners that can meet what they really want from here. And then in the next slide, which you will be able to see that at the moment, amid of our strategy 2030 finalization, and which will be launched at COP30, I wish to share with you some information about what does CRUISE provide. Basically, that could be summarized into 3 bullet points. We work with diverse early warning actors in least developed countries, small island developing states, so that they can provide reliable, sustainable early warning that meet international recognized practice. And we deliver at scale, facilitate accessible, sustained investment. We drive next generation of early warning and climate service through this innovation. And then in the next slide, you will be able to see with these 3 goals and some of the introduction that who we are, what we do, that CRUISE we launched at COP21 as part of the global climate action agenda, which you all know that same year Paris Agreement. And then we are one of the 26 financial intermediate funds at the World Bank that enable international community to pool and coordinate resources from many resources, and that's in the bank and all the other sectors. That we are specialized and dedicated to strengthen the multi-hazard early warning systems in LDC and the seeds that one of these 26 fifths that's recognized by the bank. And we also have 12 very important contributing members, and we have currently 3 implementing partners, including World Meteorological Organization, United Nations Disaster Risk Reduction Office, and the bank GFDRR. And recently that we are going through accreditation process to have ITU and IFRC as our new implementing partners, which actually this covers the full value chain, which you saw from the previous chart, and to enable us to have end-to-end product, which from the early warning to early action, which in the next slide, you will be able to see that Cruise initiative facilitates, which we have various modalities. Namely, we have 3 that to support all the ODA eligible LDC and seed country on the early warning systems and relevant services. So you see from here the pathway that start with something that provides small scale, short-term assistance and advisory service toward the country and the region in the middle of this chart to establish our strength early warning systems and services that can provide a fast-track access to the one that which arrow are pointing to the Global Climate Fund financed that through our agreement of a thing called simplified approval process, where you can access to their fund up to 25 million. So Cruise does not only fund projects, which it also helps country to prepare, access bigger climate fund as a pathway, which in the next slide, I'm going to show you in detail of each individual of this. As you can see, these are the criteria that for each of our 3 modalities, including the national and region multi-year projects. For the national ones, 3 to 5 million, 3 to 5 years, regional 5 to 7 million, 5 to 7 years, and then to the ones starting at what I mentioned for the accelerated support window, 250,000, and for 12 months. And then it can be scaled up to the GCAP simplified approval process, which this is very a good framework, which you will be able to find more details from the link below. And in the next slide, I will show you that Cruise, we have a monitoring, evaluation, accountability, and the learning framework, which to track our progress and the result to deliver at impact. Which every year we publish our annual report to document those results. That here you see some of the key highlights that we published in May or June this year for the progress of 2024 and before. So in less than a decade that we have improved forecast warning for almost 400 million people in vulnerable countries, supported 90% of LDC and seeds that are affected by fragile or conflict status, and enabled 78 national strategy and laws on the early warnings. So it proves the model is working. And now the challenge is how we can accelerate and expand, and AI and space technology can be the key driver here, which that I wish to show you one of the example in the next slide. That is a live example that actually we are running as our project in Malawi. So Malawi faced deadly storm and flood that built, but it has very limited forecasting infrastructure. So through our fast track accelerated support window for 6 months of this project, which we are piloting AI forecast in a box system, with the Norwegian Meteorological Institute, and it uses the local and satellite data to boost the lead time and accuracy for severe weather alerts. And this one, once it's validated after the 6 months of the project, which this one will be further integrated or be applied into Malawi's current multi-year national projects that for its AI-based weather prediction system, which this will further improve the current operation of the accuracy, timeliness, accessibility of forecast for the end users. So it's not the only case that I'm also going to show you in the next slide that Cruise, we also have our operational partners, and we are leveraging their expertise and potentials from our implementing partners who can actually apply and implement for our pipeline projects. And on this topic, we are happy to share examples from group on Earth observation that AI impact is multiplied when paired with Earth observation. And you see one example is that of their geogram on the agriculture monitoring. That is their global agriculture monitoring initiative that's supported by major space agencies that leverage satellite big data and AI for crop classification, field monitoring, and boundary detection, where they are interested in application of this for East Africa projects and etc. And of course, the next slide, they have another example from their satellite applications on Digital Earth Pacific program that led by the Pacific community provide Earth observation-based solution for 22 Pacific Island country and territories. So it includes time series of regional products such as coastline change, including rate of change and water presence. So these products are built using AI and machine learning tools applied to 8 to 30 years of open satellite data. So for more detail from our operational partner, you can scan the QR code and then to learn more. And then it's reaching to the end of my presentation, the last slide. My takeaway is simple. So AI and space are not just for the future technology. They are the lifeline when matched with smart financing and strong local ownership. So you are welcome to learn more from our website, which is on this slide, or directly contact us. And thank you very much. Back to you, Valentia. Yeah.
Laszlo, you can go ahead.
Yes, thank you so much. Thank you so much, Yi, because this is a really good segue to now going into space and also see what solutions we have to provide this lifeline that you mentioned from space. So my name is Laszlo Eteschi. I'm the CEO of Ateleris, and I really would like to take you here on a journey on AI in space, focusing really what we can do, all for me personally, for us to go around the term of autonomy. And so first, I would like to start off where we were so far with these really three wonderful images of instruments that are circling the Earth or pointing into the sky. And what they have is really, this is an impression for me for the AI at scale that we've discussed so far. And all these scientific instruments look at something else and they produce massive amounts of data. And they have one thing in common. They are being processed here in terrestrial data processing facilities. So we observe the data in space or maybe here on the ground. We store it, calibrate it, make a product from it, and then at the end, we can use it. Now, the point of this session now is going out into space and use edge computing in space. And so the idea is that what we've seen so far, this long pipeline, data processing pipeline, where we can also employ AI, we move this up and really run it fully or partially in space on an embedded device or it could also be not in space on a drone, for example. And the idea being that we run it there and we can then use the data right away. We've heard it before in the other session. We could do compression, for example, with AI there, and then really send down data that it's more compressed, or we can do alerting. And one example of alerting I would like to show here, this is a project that we did in the past where we basically built a data set. We curated a data set of boats and also of traffic participants. We then trained a model, or two models in this case, that would detect these objects. And what we did then, we integrate that model, we shrank it, we optimize it, and we actually put it onto an embedded device on a drone in this case, but it could also might as well fly to then really in real time detect objects and then send alerts or give out combined information that has an added value. Now, before I go more into the use cases, I just would like to bring up what the challenges are of operating anything in space. And I don't know how many people of you still remember this game from a long time ago, Oregon Trail. The idea was basically to move from Missouri to Oregon City, and it was very tough, so hardly anybody actually made it. And this would like to use this analogy just to show that space is a tough domain to operate in. We have no atmosphere, so it's very difficult to get heat away from electronics, so you may burn up, so you have to be careful with that. You may have no protection from a magnetic shield from the Earth, and there also no atmosphere, so you may have radiation damage that you have to protect yourself against. If you lose connection or contact to ground and you have no procedures in place, you may lose the instrument because you can't guide it anymore. And if you have any other software or hardware anomaly, you can't just go there, open up the instrument and fix it. So you may also have a mission-threatening situation. And these things, these issues are combined with other limitations that we face. For example, weight budgets. We can't just shield everything in massive amounts of metal because we have weight budgets. We have power budgets. Some technology is not available or not ready to fly. We then face operational challenges like long time delays, minutes and hours until a command arrives here and we can react to this, or a message from a spacecraft. Then we have limited bandwidth, so that reduces the available data that we can receive or send. And as I said, it's very difficult to access, even impossible to access these devices that easily. And so that's one thing. If you go now back to using AI on board, not all of these problems can be fixed with AI, and AI even suffers from some of those. But I feel, particularly in terms of autonomy, we can get a large benefit from it. For example, in terms of safety and longevity, we can analyze data streams on board of health information and then react to that and find out anomalies and react to them. Or on the other side, we can do new mission concepts. So instead of downloading data and observe it on the ground, we can observe it in space and then directly respond and react to that. We can optimize data returns and many, many other things. And to pick one example and go a little bit more is this one here. What you see is a plot of current, of electrical current on sticks, our instrument that's flying currently around the sun on board of Solar Orbiter. And sticks and Solar Orbiter are connected with a space wire, and we must not, under any circumstances, put a high current on there. So what we do is, because if you were to do that, we actually have mission failure. So what we do is we try to see that everything stays between these boundaries, and if you get close, we turn off the instrument. It's very simple, it's robust, it works. Now, what we could also do if you were to employ AI, this example here with this trend analysis, very simple, I understand, but we could just look at how this current is changing over time, what the evolution is, and you can then see and predict and see, will there be in the future an event where we would cross this current and we would have a life-threatening or a mission-threatening situation. And so we can predict this, and with this trend analysis, the results, we can say, well, let's alert ground early enough. For example, maybe capacitor is aging and changing the pattern of the current. We can detect this, we can alert the ground, we can act automatically, maybe turn off certain subsystems. So this is really one way to use autonomy AI in that respect for safety. Another example I would like to give here from Aurora Technologies that presented a solution where they can observe a wildfire. So they can extract now directly on board the position, the time, the intensity. And so instead of sending all the data down for processing and then analysis, they just send down the detections and alert right away. So responders on ground can receive the alert and directly react to this. And if you want to be a little more visionary, this is a program that ESA has started. They're really pushing towards a space transportation ecosystem. Now, if you think about autonomous logistics here on the ground, there's this automated pathfinding and docking and moving around of goods. And if you do this in space, we can't control it manually. It's not possible. If two components have to dock so that one component can pull the other one away or go and refuel, you need to have autonomy there. And autonomy is really something that we understand as artificial intelligence that can help machine learning models that can be employed. And so there are challenges. Some challenges are very similar to what we have when we now go into modeling. We need to train an AI, we train a model, we need data. They're limited, especially in these situations. We need to have trust. So we need to know that models are robust. How do we do this? When we execute them, we need to be efficient. I said before, thermal energy or power is not abundant. And then when we can maintain and execute it, we need to update maybe portions of it, but we can't access it. So there have to be new methods in place to really deal with it. And this whole thing is encapsulated with a trust. And trust is really the essence. If there is no trust, we can't use these tools. And so one way forward, just to pick out a few, is with data limitations, maybe we could do a more open data strategy where we share the data of instruments to really build our models and test them. And then in order to gain trust and improve robustness, we can maybe use model verification. This is a topic I'm sure the panel will talk about, which is a more researchy topic. It's not easy to do. Then when we run the models, we want to be efficient. We want to have a lot of bang for just a little buck, because at the end, we don't want to produce too much heat, but we still have to have a lot of throughput. And when we maintain it, that's at least what we always push for, is really a software-driven approach. Ensure that we have hardware, of course, but then we virtualize a lot of it and have it malleable by using software and together with these models. And all of that has to be wrapped with standards and governments to improve trust, and also maybe with test beds where we can play around with this without actually harming entire missions. And so before I let you go, I just wanted to show you this iconic image of NASA's Curiosity Mars rover taking a selfie. And I just love it because it's another way of showing how far we can get with autonomy. And I also feel this is sort of the way we go. AI will not solve all our problems, and AI is not the hammer for every nail, but I feel really in terms of autonomous systems, this is really a way to go where we can really benefit also for humanity. We talked about disaster recovery, detecting this, helping people on the ground. I think this is really a point where we can help a lot. And to build trust will be a path forward that we have to take step by step. But I think one way that can help us is to have maybe hybrid systems where we use AI to get further and to have maybe better results, and be safeguarded with classical approaches like the FDR approach I showed you with the current, where this will help and work if all things break. But maybe we can then harness the power of AI to really go further than we would be going otherwise. And that's about it. And if there are any questions, I'm wonderful to help. And otherwise, I'm just really eager to see what the panel has to say about this. Thank you so much.
Thank you a lot. Thank you, He. Thank you, Laszlo, for this presentation. So basically, if we saw that in the first session that it was clear already that we do not have a lack of information, but actually really the opposite. Now we understood even better that what we need for the future is a faster access to useful data, rapid assessment, and that AI could be really also essential in the space logistic. But there are still some limitations, some challenges, one above the trust, as mentioned by Laszlo, that we can discuss, of course, in the panel discussion. As a reminder for the audience, feel free to write your question in the chat. I saw already some pop-ups. We will discuss them at the end after the panel discussion. So let me briefly introduce the panelists of this session. You can turn on your camera and unmute yourself. So it's my pleasure to welcome Klaus Buchheim. He's the business developer at Clypsidra Technologies, and he has more than 20 years of experience in the Swiss space sector. Welcome, Klaus.
Welcome.
I also have Ludovic Monera. He's the initiator and commander of the Swiss Armed Force Space Program. Welcome. We also have Andrew Price, postdoc at EPFL Computing Vision Lab, whose work focuses on the machine learning for autonomous system. And we finish with Lars Bromley, who works with the United Nations Satellite Center, the UNOSAT, and is part of the UN Institute for Training and Research in Geneva. So Lars helped lead the UNOSAT efforts on conflict monitoring, human rights investigation, and support to the humanitarian operation around the world. And that's why I would like to start directly with you, Lars. So basically what you do also at UNOSAT is to oversee the AI development efforts. Could you share some example of how AI is used to extract value from satellite data in a way that made actually the difference on ground for you?
Certainly, yeah. So my office in the UN Satellite Center, we basically support UN operations of different kinds by analyzing satellite imagery. So we're very active on disaster response, also conflict response, things like human rights investigations, and supporting humanitarian operations. So for something like a disaster response, if a cyclone hits an area, we will have analysts basically get high-resolution satellite imagery of that area as quickly as possible, and then do a building damage assessment. So the key piece of information there is how many structures have been affected, how many of those structures are essentially residential versus business versus industrial structures, and therefore what sort of relief planning can be informed with those numbers. And this is something that we do pretty much constantly. The damage tends to be a lot more intense in conflict areas, and it can really take an enormous amount of time to get through some of this imagery through manual analysis. We also do a lot on flood response. So floods are the most common natural disaster. And we do actually have an operational AI system that ingests radar imagery from the Sentinel-1 satellites and automatically extracts water vector data out of them. And then we turn around and put those on maps and geoportals and things like that for our partners to use. Finally, things like refugee settlements and settlements for other internally displaced people. These can be extremely dynamic environments. At the height of the Syrian civil war, one of the largest refugee camps had more than 5,000 people showing up there every day. And it just becomes a huge challenge to get all those people into shelter as quickly as possible. So things like the urban planning aspect of the activity tends to fall off the wagon, basically. And again, AI can do quite well mapping some refugee settlements, depending on how orderly and structured they are. AI does well on extracting floodwaters. Things like building damage assessment, where you're often comparing two images together, which maybe are collected by different satellites and then collected at different angles. We have a much harder time with that. We have a big collaboration with Google Research right now, using one of their models called Sky, S-K-A-I. And yeah, we're working very hard to get that as an operational tool that we can use in crisis situations. But it has a ways to go until it meets our level of kind of ease of use plus accuracy. So I'll wrap it up there, but if anyone has any questions on that, certainly let me know.
Yeah, that's very interesting because we didn't touch in the first session anything about the impact on the humanitarian side. But actually, there was one question that would bring us also to the role of satellites in the crucial role in defense and security. So, Ludovic, as the commander of the space program of the Swiss Armed Force, do you already use AI in this program? Do you have an example that, for example, related to security?
In fact, yes, we identified more than 10 years ago the necessity to have AI on board on satellites. Why? Because when you have to support the tactical level within armed forces, tactical level needs information which are absolutely fresh. It's a question of minutes, if not seconds. And what have been mentioned earlier, that all this pipeline of different activities, if they have to take place on the ground, and if you have to wait for the next overflight, you send your data on the ground, of course, it would be too late. Could be useful for the operational level, the strategic level, but not for the tactical level. That's why we focused ourselves on the developing of new capabilities, and we introduced in fact, the use of AI for the detection of rocket launches a couple of years ago, 2021. We chose a certain number of launch pads around the world with fair weather conditions, with conditions allowing to have one picture a day, an optical imagery, satellite products. So we tested a lot of things, and we decided to use one commercial product, which is the Planet Scope of the American company Planet, in order to have one picture a day of certain launch bases around the world. And we used a platform developed by a Swiss company to train the algorithm in order to detect the signs of an upcoming rocket launch. And in the beginning, it was quite difficult because, of course, you have this problem of trust and especially of knowledge of what's really happening on the ground. At least you have ground truth. You know when the rocket has been launched, so you can come back into time and then to have some patterns being identified. In the beginning, there was a rate of false alarms of 50%. After a couple of months, after 6 months, in fact, with the training of the algorithm, we reached a rate of false alarms of 9%. That means in 91% of the case, the algorithm was able to announce a couple of days in advance the preparation of an orbital launch. It was quite interesting, and those are exactly the things that you need in the future in order to support the armed forces in the planning and the conduct phase. But it has been done on the ground. The step, of course, to be done is to be able to do that in space.
That's very interesting. So, I mean, onboard processing would help definitely in several cases. So, Klaus, in your experience, so Laszlo also mentioned, for example, efficient computing. Do you agree that this is an important aspect together with the onboard processing, as Ludovic was mentioning, and how the software, in your case, as a framework provider or hardware, can help with that?
No, absolutely. Because I think what Laszlo also hinted to, right? The environment in space is completely different. What can be done with AI, right? We don't have racks of GPUs available to run hundreds of models and terabytes of data memory, right? So we need to look at different compute and processing approaches to get the capability there, and approaches like ours, right? Using software-based acceleration combined with lean models, and the models absolutely help and is required. And I think also Laszlo in his presentation also highlighted slightly different things, and I think also Ludovic mentioned to that, right? The use of AI in space is very different than on the ground. It's not about this 10-year time series data analysis to be performed suddenly on board of a satellite, right? It's quick information extraction, early information, and then turn this either into an action for the satellite to be done, right? So the satellite identifies preparation for a rocket launch, and then maybe commands already the next satellite 1,000 kilometers in the back to redirect its instrument to actually take a closer look, right? And that would be the type of autonomy we're looking at. And it's very different than what we heard also this more before, right, in time of this climate change. And all of this needs fast data processing and the trust environment that you have platforms from the hardware and software side that are trustable, so that then the different AI applications can build on top. And I think, Andrew, you are working actually on making also the AI reliable in space.
Yes, absolutely. So just to emphasize the points you're making about lean neural networks, a typical GPU that we use for training neural networks on the ground might use 250 watts. But then when you go to put it on a CubeSat, you're in the range of 5 watts. We're several orders of magnitude difference. So it's not a simple matter of taking a state-of-the-art algorithm and applying it to the space environment. And I completely agree with you about getting the quick turnaround, and the way we process the data is different. Because as Laszlo also alluded to, this is not using AI is not a binary state. It's not AI versus classical. We can have a quick process performed by AI, and it can say, hey, I think this image is interesting, and then that gets priority. And then you can immediately get the ground operations focused on potentially high interest information, but we still have that separate data stream, which could be then we can get to it again later. So it's not a question, I think, of AI versus classical, but it's a question of where these tools can be incorporated in to provide the best value.
Absolutely.
Ludovic, I saw you wanted to say something.
Absolutely. In fact, I'd just like to go further. That's what Klaus has been just saying. For us, a very important thing is that to be able to connect the satellites with each other and not to rely on the ground segment to transmit, the need for an updated coverage or to use another sensor. Our perspective is to use mainly 3 different types of sensor. The best sensor, the best vacuum cleaner from space is electronic intelligence. You may detect a lot of things. You generate a huge amount of data. When you know exactly what you are looking for, you may find it. And you have the opportunity to locate it, sometimes even with only 1 satellite, with a precision that is high enough to task another satellite to take a picture of it. And when you take a picture, of course, an optical imagery will be compatible only with fair weather conditions, or even during the day for some kind of sensors. If you don't have that, you should task a radar imagery satellite. And maybe on the radar imagery satellites, you can get some echoes or other things or jammings that allows you to task the electronic intelligence satellites. So you have all those kind of different sensors that should be able to talk to each other, be it on different satellites, talking to each other through relays, maybe geostationary, maybe on medium of Earth orbit, or different payloads combined on the same satellite and talking to each other inside of the payload and working this way during the same overflight. Those are the things that we are looking into, and we are trying to develop that, including with some Swiss companies.
Yeah, Andrew, please go ahead.
I want to jump on that as well, because I agree that there's all these different modalities of data, and they can come from different sources. And I think we have a large problem. It's almost political, though, in the sense that we can't necessarily access data from person A and then person B because there's all these sensitivity requirements. And a large part of the computer science community, a large number of these milestone breaking developments have been also attributed to this idea of big data, where we can now apply these models to a large amount of data. One project we have at the Space Center is we're actually analyzing these observatory images for streaks, and they go back tens of years, where we can look at, and now we have these data sets where we can identify objects, and we can use this to train models that could perhaps be operating in real time. So I think there's some hurdles to overcome there, but there's more data than we think there is, even as challenging as it is to get any data from space.
Then let me go back, Ludovic, to a question for you, because during the presentation, Laszlo introduced the problem of trust, right? So, and I guess that when we're talking about security and defense, innovation is of course very important, but has to be balanced a bit. So, is this a challenge for you right now?
Well, it's a huge challenge, in fact, because when you have to act fast without trust, you will do fast a lot of mistakes, and the mistakes will be impacting you and maybe some other people as well. The only way to have trust when you don't control the software itself, which could happen, but still that would be a good way to have better trust, is at least to control the data that you have been giving your algorithm to be trained. And for us, as an armed forces, the best data you have is to use your own formations, your own units. So you take a picture, you take some eavesdropping data from your own battalion tanks or air bases and so on. You train the algorithm to recognize, to identify, to pinpoint the things which are important for us. And then, of course, you check, you double check, you triple check, and you let, of course, afterwards, the troops using that and be able to see themselves from space and to be sure that, okay, that has been rightly identified as a main battle tank, that has been identified as a logistical depot, and so on. So the ground truth begins with the reality, and then you can try to use this algorithm, this training, with just this training for other areas that you don't control.
Klaus, you want to go over?
Yes, if I want to jump in, I think also an element of trust is breaking up in the end the problem a bit. And this is also something we're looking in, and I think we're also ESAN event goes right into type of a modular architecture where you can say, well, I trust the hardware platform because it's radiation hard, so the element of failure is low. I trust the operating system running on it. I trust the AI inference engine running on it because they have been ESA certified, right, ECSS. And then it's in the end, right, it's just the model, right, that maybe you need to trust together with the data trust that Ludwig mentioned. But at least the things run on a trusted platform in a trusted environment, right? And again, I think, Andrew, you're working on things like also making the models more robust, and that will level, again, an element of trust so that the environment in which then the data is processed is trustful. And I think that will also help in building that trustful environment, right? That this type of processing is reliable. In a sense, AI can be reliable.
Yes, on that idea of trust, and Laszlo so wonderfully identified all these different ways that these networks can fail, and we can address each of these. We can inject faults into our networks and see how they respond. We can also run uncertainty wrapping algorithms to see that here's the bound of the envelope that's coming out. And we can also modularize these parts so that we understand that this specific tool behaves in this way, and then we can add it into our trustedly built pipeline.
Let me go back to Lars. Lars, do you share the same difficulties, or do you have different challenges? Let's put it this way: different problematic to solve when using your models.
In terms of trust?
Yeah, for example, or if you have experience with different challenges at all, what is the biggest challenge for you?
Funding. There's never enough funding in the UN system, and this year is particularly bad, which leads to a shortage of analysts, which would nominally increase our reliance on AI tools, but those can be also very expensive to develop. There is a lot of difficulty with, sharing like the secure UN information with, things like ChatGPT, just like a lot of organizations have. Maybe someone you don't quite realize is running all the classified information through ChatGPT without understanding what that really means. But for us, not so much. We don't do any of our more sensitive investigations on anything outside our own network, basically. Where we would really benefit from AI would be some of the larger scale things, which everybody knows about anyway. So destruction in Gaza, the Syrian civil war, the Ukraine war, stuff like that. But within the context of those, we wouldn't be using AI on any of like the human rights investigations or any of the things along that route. So we're pretty safe as far as satellite imagery goes. But yeah, there's kind of the broader context of the usual people thinking tools are free when In fact, they're not free. You're paying for them with whatever information you're giving them.
Yeah, that's very true. And this would go back then to Klaus, because you, Klaus, have 20 years of experience. You have experience with the space agencies and with the industry sector in the big space sector. So the point is, seeing your experience also with Airbus, for example, Ateleris Space, how can institutions really accelerate the adoption of AI in operational space mission, with ensuring actually the trust? What's the best way to bring AI also in these big industries?
Well, I think that it's basically in the end it's the work of being something like an anchor customer. And I know, of course, it's difficult with public money, right, in some aspects, but the use cases that Ludovic, for example, highlighted, right, if they then actually would be implemented, it gives then the actual use case, right, where we can prove and show that the technology is working, which then again either opens the room for other institutional customers to say, hey, you see, it worked on mission X in an operational environment. It's ready, we can use it, we see the benefit. And I think that next to the R&D work that is funded by ESA, that this step going out from R&D, and I think that's where we are right now with AI on board, a lot of things are there, right, into saying, okay, now we put this actually into an operational use case. I think that is a critical step to then really show how is it used, where is the benefit, right? Maybe where's not the benefit, right? Because not everything we think might work or what the benefit is. And I think that's the critical step, because from an industry perspective, and even R&D, this is something we cannot do, right? If we're not actually building ourselves these type of systems in space.
That's very interesting. And Andrew, I would like to ask you something else, because now we discussed a lot about the trust, how to the pre-processing. But Lazo, for example, during his presentation, he touched also the space logistics and some additional challenges related to the environment itself, right? So what's your opinion on these? Is it something that can be solved easily? I mean, I'm thinking about the solar radiation, the power consumption. What's your impression? What's your feeling?
So that's actually my current focus right now, is I'm seeing how different neural networks respond to the effects of radiation. So I'm building a model to inject faults that are basically, if you get hit by a high energy particle, then you might have a bit that gets flipped, and now suddenly your model isn't what you put in there. And basically seeing how robust this model is to those faults that are injected. I don't have an easy question about how easy this is to resolve. There's some scaling factors. Larger models seem to be a bit more sensitive. The approach thus far, of course, is radiation-hardened hardware, where we encase it in some protective shielding, but we have these weight restrictions, so that's not always the option. I think with neural networks, they tend to be a little bit over-parameterized, even for smaller cases. So I feel that there's always a little bit more performance you can squeeze out of them in terms of making them a little bit more redundant and perhaps more resilient to a radiation fault, or perhaps perform a secondary task like estimate how accurate it thinks it's doing. So I think there's a lot of opportunities for improvement there. And I guess I'm optimistic, if that answers your question.
That's very interesting. Thanks a lot. So I will stop here with my question, and I would like to have a look at the question and in the chat. So there was one question for Ludovic. Actually, I don't know if you can answer. So was there a difference in the error rate? So it's about the case of the missile launch detection. So the question is, was there a difference in the error rate between the wrongly detecting a missile launch and not detecting a launch that actually took place? And how did you train the model to prefer one error over the other?
In fact, I think if I remember that well, it was more a wrong detection. So alerts of missile, better said rockets, it was orbital rockets, rocket launches that didn't take place. But sometimes, it maybe it wasn't that wrong. Maybe there were some problems in the preparation of the rocket, and the rocket has been then delayed. The launch has been delayed for a couple of days. That's the reason why we tended to focus on have a larger time scale, and to say, okay, the model has to be able to foresee the orbital launches in between 3 and 7 days, because that's what usually would be the case. And for this launchpad, this special launchpad we used as a main effort because it was very active. There were also some crewed mission. There were some human being sent into space. So for that, there is a backup. There is a second rocket being ready with a backup crew being ready to help the first crew if there's some problems in space. And of course, that's a subtlety that you have to give to your algorithm, so that not to be wrong in the interpretation. So I think that's what the main lesson for us was following. You can train your algorithm; it will work up to a certain point. Yeah, the training is never over. It's like with a horse, by the way. Every day, every use is a training, and you have to be ready to correct, to do, okay, it's right, and okay, it's wrong, and to do that every time, because of course things are changing. Some actor can adapt their procedures, they can try to fool your algorithm, and so on.
Thanks, Ludovic. There was also another question, which is about, I'm reading out loud. So with satellite internet providers like Starlink, is there any plan to have new space devices connected to a protocol that works low millisecond communication with the ground? Laszlo, do you want to try?
I can, I'm not sure if I fully understand the question. I'll try to interpret it. I think there's 3 ways. One could be understood if we could use these in-orbit networks sort of as a backbone for communication. I think that's probably going to happen as well, that we have this, Ludovic also said it, this network, and we don't rely on the ground station. Second interpretation, if you say it's about a question about AI, if we could use AI to improve signal quality, and going towards 6G. And Klaus and I had the opportunity to look forward to working together on that. The idea being to having a network, to having antennas that actually target and improve targeting while flying over, and so to use AI to optimize basically targeting to the ground, predicting, for example, where a high-speed train would go, so that you are ahead of your time instead of lagging behind. So that could actually really improve reliability and connectivity. The last bit, if we were to interpret it as going into deep space, as I said during my talk, we could venture out and we have this delay. I think there we will always have to work with delay. There are some physical boundaries, the speed of light, and there's going to be a hard way around that. So if our instrument, if 6 on solar orbiters flying around the sun, the travel time is a few minutes to get there and back, no antenna, no AI will change this.
Thank you. So at the moment, I don't see any other questions. So maybe I would like to if there's no other question, we still have some time. So maybe what I would like to ask our panelists is like take home message. So if you can think about a way to what would be the single most important thing that needs to make AI in space become an asset. So I understand you're talking with Ludovic is about sort of trust, and talking with Lars is more about okay, also having funding and being able to trust in the tools. But what would be, in your opinion, the most important things to really have been able to adopt AI in space? Who wants to go first, Lars? I saw that you unmute yourself.
Oh, whoops. Yeah, no, I mean, for something, I mean, yeah, we deal with a lot of different kinds of analysis. You know, Some of it is much more on the remote sensing side, so water extraction, and then land cover mapping and things like that. For things like the water extraction, if that happened on board a satellite and then the water vector data was just downloaded to us, that would certainly be good. It would save us a couple hours at least, just in terms of how long it takes that image to get downloaded to European Space Agency or wherever, how long it takes it to get added to their portal, and then how long it takes us to download it and run our analysis on it. So you wouldn't, it wouldn't be a massive change, but it would nicely cut some corners and save some time. Same thing with land cover mapping, but we don't usually do that in crisis mode. Some things like refugee mapping, where you're using a single image, again, if it could just be processed and the vector data given to us, you would save some time. But when we start talking about multiple images from multiple satellites, comparing them together to do things like damage assessment, yeah, that's where my imagination fails me. I can't imagine it's anything close to, a Maxar satellite receiving an Airbus image from an Airbus satellite, doing the analysis on the Maxar satellite and then down to us. Technically, that's a beautiful workflow. Legally, license-wise, that's about $40 billion in negotiations that would have to happen between Maxar and Airbus. Okay, 40 billion is a bit high, but
Ludovic or Andrew, yes, if you want to add something.
Sorry.
Well, there was a question, in fact, been asked, and that joins a little bit what I would like to say. If we are still on the experimental way of the RSLM real use, I think right now there are some countries doing some real use, operational use of AI, especially China and the USA. In Europe, it's still mainly experimental, and those things are mainly classified. So we think that they are doing that, and in fact, the main point should be this one: we should be very cautious using transparency and clear ethical values with AI, because if you have those capabilities to detect things, to pinpoint things, to transmit coordinates, and so on, quite soon you are coming in a robotic warfare. And that's exactly the thing that we have to avoid, to prevent machines fighting machines and have human in between. So this whole acceleration of decision cycles, AI brings a lot of value to those things, but we still to have a human in the loop for every crucial activity.
Andrew, you wanted to add something?
Yes, I actually agree with that sentiment. The aerospace community, compared to other communities, I would say is an extremely conservative community, which is a good thing. These are very expensive projects. There's potentially high risk involved, and that can lead to some strange things. I know in some search and rescue applications, they'll have a camera and it's attached to some system, but instead of compressing the images, they just fiber optic it straight to the back. They don't want to ask any questions about the compression and uncompressing. So you just want to remove all those question steps. And right now, the way we are treating these machine learning models is they're essentially black boxes, and we have lots of questions about what they're doing. So you asked what my message was, and I really do think that machine learning is a key to unlocking a future of autonomy. But ultimately, if we're going to insert these tools into the pipelines still need to be human built. They still need to have logical flows. The physics have to be followed. And ultimately, I think we have to de-risk and try to open up how these models are working and what we can expect from these models before we start inserting them into a decision-making pipeline.
And I think from my side, I think that actually the two aspects. I think what I also saw today in the discussions, right, is really have to think of AI in space differently than AI on the ground. Again, it's not about data analysis and things like this, right? It's more about autonomy, certain elements of helping early alert the informing. It's a different type of capability to think. And I think that also needs to help in the thinking process, right? For what to use the AI in space, for where is it really beneficial given the space environment and the constraints we have. And then I think in the end now we're at the stage of making it happen. And of course, fully shared, right? It's not, hey, hooray, we now have everything and let's just go and give it a try. It's the careful steps. But I think we have to make a step now because a lot of the building blocks that we discussed are there, right? We're building the trustworthy models. We're getting there. The environments are getting there from the computer environment. And I think we can make now the first step. As we said, right? The journey starts with the first step. And so far, I think we've not really taken the first step, but let's do the first step. And then we can still decide if we want to walk or run.
Thank you, everyone. So time is over, so perfect on time at 4 o'clock. So thanks a lot. I would like to close this session. Thanks all the speakers, thanks to all the panelists for this very insightful discussion. We hope we give you food for thought, and let's see what the future research will bring. So thanks again to everyone. Thanks also to the Swiss AI Weeks team who hosted our session, and have a nice weekend.
Thank you very much.
Goodbye.
Thank you for giving us the opportunity.
Thank you very much.
Thank you.
Amazing,
Thank you.
interesting session.
Yes.
Thank you all.
Thank you.
Thank you.